Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show safety heat transfer analysis through a fire tube boiler. This is the fire tube boiler. This is used for producing steam, and this is especially used in small houses in cool regions, right? And for understanding the model in a better way, let us have a segmented view of this one. We can cut it from different planes. Let us cut it from front plane and see the geometry. You can see here. This is the inlet of hot flue gases. It will be passing through this inside tube, and finally it will be obstructed at this location, and after being obstructed from this location, it will be coming out from these different pipes. All these pipes or tubes are made up of copper, and at this opening it will be again obstructed by this front plate, and it will go out from this way. And all these tubes are surrounded with cold water, which is fed from this one. And as hot flue gases will be passing through these tubes, and the tubes are surrounded with cold water, these waters will be warmed up, and finally we'll get steam from this water, and that will be collected from this opening, right? We can cut this from different plane also. Let us cut it from some other plane. We'll cut it from right plane and see the view. Let us have a segmented view from this one. You can see from here, if we have a segmented view from right plane, it is not clearly understood. Let us have some rotation of this one. So the things from this one, hot flue gases will be passing, and from the back side it will be coming again through these small dia tubes made up of copper, and the tubes are surrounded with water. Water will be at these locations. So water will be warmed up, and by the same time you can see outside you are having some kind of space, and this space is actually maintained for insulation, and at the top side we have provided one kind of insulator, right? So the geometry is clear. Now let's start our simulation. For starting this simulation, we need to create flow simulation environment, and that will be started with wizard. We're keeping the name of the project as project 2. Next to that, we need to select units, and we are considering SI units here. It is a heat transfer problem, so we'll consider temperature as in degrees centigrade. Next to that, we need to select type of analysis. It is an internal analysis. And from physical features, we need to select fluid flow, and it is conduction definitely. And in this case, gravity will be involved, and the direction of gravity is indicated by Y here itself, which is in the upward direction. It will be minus 9.81 meter per second square along Y direction, and along Z it will be 0. Next to that, we need to select fluids or gases. Gases, it will be flue gases. It is consisting of carbon dioxide, carbon monoxide, and different components. Here in this case, for simplicity in our analysis, we'll consider this one as air at a higher temperature. Okay. Next to that, it will be air, and also we need to select some fluid also, and fluid will be water at a normal temperature, right? We'll select water and air as the main fluids. Next to that, we need to select materials. Materials are made up of copper and insulators, right? Let us select copper for metals, and insulators will be selected during application of boundary conditions. And here in this case, we are considering default outer wall thermal conditions and roughness. And finally, we need to select thermodynamic parameters with pressure as 101325 Pascal, and temperature will be 30 degrees centigrade, that is normal temperature. And solid parameters will also be the same one, it will be 30 degrees centigrade. Let us finish this. Now it is showing computational domain. We can hide this domain for applying our boundary conditions. Let us hide computational domain, and we need to select different fluid domains. For selecting these fluid domains, it is better to have a segmented view, so we can cut it from front plane and provide specific locations, right? Now we need to apply boundary conditions, and for that, initially you need to select fluid subdomains. Here having 3 different fluid subdomains. Insert fluid subdomain. Hot flue gases will be provided from this opening. So we are providing hot flue gases at a temperature of 1600 degrees centigrade. Green check. So this is first fluid domain. Next one, we have to select 2 more fluid domains. Insert fluid subdomain. From this opening, we will be providing cold water, and let us select from here. It will be water at a temperature of 30 degrees centigrade. We will provide cold water from this opening, right? Green check. And another fluid domain is needed. That means for insulation, we need to provide air at this opening, and outside we are providing one kind of insulator, right? So that fluid domain to be also provided. It will be fluid subdomains. Insert fluid subdomain, and it will be air at a temperature of 30 degrees centigrade, normal temperature. We need to select that location. Yeah, this is the air domain. Right, we can see. Green check. All the fluid domains have been selected. Next to that, we need to apply solid materials. Insert solid materials. Predefined. It will be made up of metals, copper. Let us select all the materials from the geometry itself. You can select it from solid geometry also. All materials are made up of copper. Only the leg and the outside surface is made up of insulators. You can select all the components from here itself. And from these things, legs are excluded. Insulators to be also excluded. Let us select insulators. Yes, this is insulator, that to be also excluded. 4 legs and 2 parts of insulator will be there. So insulator 1 and leg 1, these 2 are excluded. Excluding that, all are made up of copper. So accept this one with green check. That means we have provided copper for all the materials, and next to that we have to apply insulator for the remaining parts. So solid materials, insert solid materials, and we need to provide from here predefined gases and minerals, and it will be insulators. Let us select the components made up of insulator and the legs also. Green check. Both the materials have been defined. Next to that, we need to apply our boundary conditions. For better selection of these boundary conditions, we can have a segmented view of this model. We can cut it from different planes as per our requirement. Let us cut that model from front plane. Green check. Now we need to apply different boundary conditions. First of all, we need to apply hot flue gases from this opening, right? So boundary conditions, insert boundary condition. And we're planning to provide mass flow rate from this one at a specific rate. Inlet mass flow rate from this opening, it will be 1.5 kg per second. And thermodynamic parameters, it will be definitely 1600 degrees centigrade. You can see it from here. Green check. First boundary condition is applied. Next to that, we need to apply cold water from this opening, right? Boundary conditions. Insert boundary condition, and we need to provide cold water from this opening. And mass flow rate in this case will be considering a little bit of less. Let's consider mass flow rate of 1 kg per second from this opening. And temperature, it will be 30 degrees centigrade. Green check. Two boundary conditions are applied. Next to that, we need to apply other boundary conditions, that is atmospheric pressure at the exit locations, right? So insert boundary conditions. It will be atmospheric pressure at different exit locations. Select this one. This is the location of exit of steam. It will be environmental pressure. Green check. And again, the exit of hot flue gases should be selected. Insert boundary conditions. It will be atmospheric pressure and the exit of hot flue gases. Let us select that one. Green check. Done. All the boundary conditions are applied. Next to that, we need to select some goals. In our case, we can select a lot of goals. We need to have temperature of cold water to be 100 degrees centigrade or something else. Like we can have steam, it may be more than 100 degrees centigrade also. Let us have it from goals. Insert surface goals. It will be average temperature of fluid at the exit of cold water, this one. And also want to have average temperature at the exit of hot flue gas also. We can have separate goals for each of them, and we can rename this one as average temperature of fluid at cold water exit. And the second one, we can rename this one as average temperature of hot air at exit. Similarly, we can have some other goals also, like insulated temperature inside and outside also, or outside the shell. Let us select that one also. Goals, insert surface goals, and to have average temperature of fluid at the outside surface of this shell. We can rename this one as average temperature of fluid outside the shell. And also we can have another one, last means, that means average temperature of fluid at the inner surface of this insulator. We can rotate this one for better selection. We need to have the location here, that means we want to have temperature of air at the inside surface of this insulator, right? So goals, insert surface goals, and it will be average temperature of fluid at the inner surface of insulator, right? Select this one. Green check. And we can rename this one as average temperature of fluid at inner insulator. We have selected 4 different goals, but our main aim should be average temperature of water at exit. That means we want to have steam at the exit location, right? Okay. So all the goals are defined. Now we can go for running. We have already run this simulation with the same data. Let us see that one from here. First of all, we want to see cut plots of pressure, temperature, etc. from different planes. For viewing these things, let us make the model transparent. The model is completely transparent. Now we can see the dynamics of flow particles and also different cut plots of pressure and temperature through different planes, right? First of all, we want to see cut plots of pressure distribution from front plane. Insert cut plots, and we want to see pressure and temperature distribution. Initially, we'll see temperature of fluid through front plane. Let us view it. You see at different locations, temperature distribution is different. You can see it from front plane. Let us have a view of this one in a different way. Let us play. This is how hot flue gases is flowing from entry to exit. But at the same time, you can see the temperature distribution of water also. Next to that, we will see pressure distribution from here. You can see pressure distribution is that much of change is not available. Clear and hide these things. and we want to see this pressure and temperature distribution from right plane. Insert cut plots, and you want to see this distribution from different plane, right? We select from right plane, and we can drag it a little bit inside. Done. Let us rotate this one to see this one. Yeah, this is the distribution of pressure from right plane. Let us see these things in a different way. I mean, we can see this one in the form of animation. Let's play. This is pressure distribution through the fire tube boiler. We cannot see that much of changes in pressure, but there will be definitely changes in temperature and velocity distribution also. Let us see this in the form of temperature distribution. Temperature of fluid, grain check. See, initially temperature at the inner shell is very high. It is in the range of 1638 degrees centigrade, and surrounding these tubes we're having water. That water also, it is in the range of, you can say, at different locations downside temperature is little less and outside it is higher. It is in the range of 19 to 199 degrees centigrade, and we can have a specific temperature from different cut plots. Let us close it. Clear and hide. Next to that, we want to see surface plots. We want to see temperature distribution through all the surfaces. Insert surface plots, and we want to see temperature fluid with all faces, and different faces temperature distribution different. This is the location of inner shell where temperature is very high, and at the outside surfaces temperature is varying at different location. It's different, right? You can see it. Let us clear and hide. Next to that, we want to see dynamics of flow particles. This is very important one. It will show the distribution of these flow particles throughout all these boiler parts. Let us see dynamics of flow particles from here. Let us play. It will be better to see from front plane. You can see that hot flue gases are having red colors, which is the high temperature of 1600 degrees centigrade, and surrounding these things we are having cold water. We are feeding cold water from here, and finally cold water, after being heated, it is coming out from this opening, right? Let us see this one in a better way. Let us clear it. Clear and hide. Next to that, we want to see our goal plots. Insert goal plots, and we want to see all the goals, and all the goals can be transferred to Excel. For better understanding, we can transfer all these results to Excel. These are the results data. First one we'll see. This one is showing average temperature of air at inner insulator. It is in the range of 272 degrees centigrade after 472 numbers of iterations. Average temperature at the inner surface of insulator is 272 degrees centigrade. Next one, it is showing average temperature of air at outer shell surface, and this value is in the range of 250.12 degrees centigrade after 477 numbers of iterations. Next one, it is showing average temperature of cold water. That is our main aim. It is showing after 477 numbers of iterations. Average temperature of cold water is 75.53 degrees centigrade. And The last one, we can see the average temperature of fluid at exit. That means the temperature of hot flue gases. It has come down from 1600 to 1047.52 degrees centigrade. So you can see the main thing is here in this case, exit of hot air and exit of cold water. There is huge amount of difference in temperature. Initially cold water temperature was 30 degrees centigrade and finally it has come off in the range of 75 degrees centigrade approximately. And by the same way, the flue gas was having temperature of 1600 degrees centigrade. It has come down huge amount, and final temperature of this one is actually 1047.52 degrees centigrade. Let us close it. You can view all these things in the form of graph also together. Next one, we want to do some kind of parametric study. Like before going for parametric study, you can see all these results together that will be obtained from goal plots here. Again, you can see all these things, insert goal plots, and when you see all these goals together, and that can be viewed in the form of graph also, summary, and when you see in the form of history. Let us view these things together. First one is average temperature of fluid at exit. Initially it was having temperature of 1600 degrees centigrade, and after 477 numbers of iterations, it has come down in the range of 1047.65 degrees centigrade. And average temperature of air at outer shell surface, initially it was 30 degrees centigrade and finally it has come up in the range of 473.25 degrees centigrade. And finally, average temperature of air at the inner insulator surface, it is in the range of 473 degrees centigrade. Right. Next one, we want to go for some kind of parametric study. If you want to increase the temperature of cold water, that means if you want to get steam, we need to provide higher amount of flue gas. We want to provide flue gas at a higher rate. Initially, we have provided flue gas at a rate of 1.5 kg per second. If you want to get the temperature of cold water to be increased, in that case, the rate of flue gas to be increased, right? Next to that, we want to go for some kind of parametric study. We have already undergone one parametric study. This is design of experience and optimization. Let us see what did we do. We have selected different ranges of these input variables. In this case, we have considered the temperature of hot flue gas as the input variable, and we have considered the range from 0.1 kg per second to 2.5 kg per second. That means by varying the mass flow rate of flue gas, we are going to see the difference in other values, right? So we are considering the mass flow rate of hot flue gas in the range of 0.1 to 2.5 kg per second, and with that variation, we're going to see the results. So we can see the results from here. It's the goals, and let us view it from here. That when mass flow rate of flue gas was 0.1 kg per second, in that case, you can see the temperature of cold water, it is 38.22 degrees centigrade. We are mainly bothered about to see the temperature of cold water, so other parameters we are not considering. When the mass flow rate of hot flue gas is 0.1 kg per second, you can see the temperature of cold water is 38.22 degrees centigrade. That is the average temperature at the exit of cold water. And if we are increasing the mass flow rate from 0.1 to 0.25 kg per second, in that case, you can see there is a huge increase in temperature of cold water. It has come up in the range of 58.55 degrees centigrade. When mass flow rate of flue gas is 0.5 kg per second, in that case, temperature of cold water exit is 79.62 degrees centigrade. And when mass flow rate of hot flue gas is 1.5 kg per second, in that case, you can see temperature of cold water at the exit is 91.24 degrees centigrade. And when mass flow rate of flue gas is 2 kg per second, in that case, you can see the temperature of cold water, it has gained huge amount. It is 115.8 degrees centigrade. That means it will be steam. And when the mass flow rate of hot flue gas is 2.5 kg per second, in that case, you can see temperature of steam, it is in the range of 156.02 degrees centigrade, right? So from this data, we can understand that if you want to get steam at a temperature of 100 degrees centigrade or more, our mass flow rate of hot flue gas should be more than 1.5 kg per second, and it will be less than 2 kg per second. So with this specific range from 1.5 to 2 kg, you can have another goal optimization. And suppose you want to get the temperature of steam to be 100 degrees centigrade. In that case, you can have another parametric study for goal optimization. And in that case, you need to select the range from 1.5 to 2 kg per second, right? We're not doing that analysis. So with this specific range, you can go for some kind of goal optimization, right? With this one, we can conclude our today's analysis. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.